Hello and good day. We bring to you our friend silicone. Silicone is a valuable material for its diverse and useful properties. It has low thermal conductivity, it has the ability to repel water and form watertight seals, and is resistant to oxygen, ozone, and ultraviolet light, making it widely used in the construction industry. It's used in coatings, fire protection, and glazing seals on the windows. You might ask, where does silicone come from? Well, silicone is simply a plastic product made of silicone, carbon, hydrogen, and oxygen. Its primary ingredient is the vastly abundant element silicon, not to be confused with the building material silicone. Sand is the natural resource for silicone. Sand's main ingredient is silicon dioxide. Silicon is the second most abundant element on the Earth's crust, making up about 27% of it. And you might wonder, where is silicone made? Well, primarily it is done in China at about 40% of the production. Then we have Europe at about half at 20%, and North America follows at 15%. Okay, a little history about our friend silicone. During the Stone Age, quartz and silica-based stones were fashioned into tools to aid survival. Then, the ancient Romans started turning sand into glass, and from there on the technological evolution was simply unstoppable. And by the 1800s, pioneering chemists discovered how to gain silicon from the sand through extraction process that will be later explained in this video. Silicon, as we said before, is the basis of silicone. And in 1823, a scientist by the name of John Berzelius isolates silicon in its elemental form. This is huge. And now, the 1940s. A scientist by the name of Frederick Stanley Kipping was the first to achieve extensive synthesis of silicon compounds and coined the name silicones. He is considered to be the founding father of silicon science. And that brings us to the 1980s. With horrible hair and ridiculous fashion, silicone played an integral role in the advancement of computer technology, telecommunications, and other related fields that rely on the microchip. Without silicone to protect products from extreme temperatures and contamination, we would not have many of the technological and electronic innovations that we take for granted today. And now, the process we've all been waiting for, but really couldn't care less about. The manufacturing process of silicone! Bear with me and we'll make it quick. When producing silicone, we start with four main ingredients: methanol, HCl, silicon metal, and other minor ingredients. These four items go through distillation process, either through methichloride or by reaction refinement. Our resultant is four very difficult to pronounce chemicals: fluorosilane, methylsilane, phenylsilane, and vinylsilane. From these four products, the silicone production process takes one more means of distillation: another reaction refinement, or hydrolysis polymerization. After this stage, we are left with five forms of silicone: silicone gas called silanes, silicone rubbers, fluids, liquid rubbers, and resins. Silicone is so useful. Some of the primary uses of silicone include electronical, household, automotive, mechanical, medical, and construction products. Some say silicone, I say silicon, because there's simply so much you can do with silicone. Which leads to the case studies where silicone is pushed in ways advancing the built world we live in today. Our first precedent is brought to us by Nameless Architecture and their traditional door with modern materials. First, liquid resin is poured into a grid-shaped mold to create the raised frame of the door, while a shallow layer of silicone was set into the resulting squares to create the panes. The elastic properties of the silicone mean that each pane is slightly flexible and reverberates when touched. The door's acoustic properties contribute to sound absorption to detract from reflection. Next, we have René Vos silicone concrete. By combining concrete with silicone rubber, a contrasting material is created. The designer has managed to fuse concrete and silicone to produce a composition of opposites. The material has both heavy and light elements and is both translucent and opaque. The rough meeting of the two materials gives an organic look to the final product, fusing soft and hard. Next, we have Volvo's Pure Tension Pavilion. This tensile pavilion is covered in solar panels that can be used to charge an electric car and then be folded up to fit in its boot. The pavilion is an interesting precedent because it's not very apparent that silicone plays a major role in the design, but the car charging pavilion uses photovoltaic panels which use silicone as a main component when absorbing sunlight.
Here we have failed case study, 20 Fenchurch Street, aka London Walkie-Talkie, aka Walkie Scorchy, aka the building that melts cars. Due to the structure's concave curve that was intended to maximize square footage on higher floors, it in turn angled the sunlight directly down onto the street below, melting cars parked beneath it. In this particular case, we have a failure in the glazing where silicone is used as an absorber of light reflection. It is uncertain if silicone alone has the potential to detract from the reflection to such an extent, but it is with this error that we look for other avenues of resolution.